Welcome to the Argmin video channel. We are in the real analysis course, and we're on lecture 3 on the least upper bound principle. So from the last video, recall that x is bounded above if there exists M and R in the real such that for anything in that set, x is less than M, and we call M an upper bound. Also, x, let's call that number 1, x is bounded below if there's an M in the real numbers such that everything in x is less than, or larger than that M, or is that M, and that's called a lower bound. Should write that down. Is a lower is upper bound. M is a lower bound. So 3. For a non-empty x bounded below, we define this thing called the infimum, but instead of that fancy word, it's just really the smallest upper bound, or the least upper bound. And similarly, for something that is bounded above, the supremum, or just write the sup, is just the greatest lower bound. So we define these things. Let's look at some examples now. Oops, I don't want to share it just yet. So example A being this set, the supremum of A is equal to the 87, is equal to, what am I saying, is equal to 87. That's also the max of A. The infimum of A is equal to -1. That's also the min of A. So from this example, you might think, well, aren't sups and infs useless? Because you can just use the maximum and the minimum. Well, we have an example to clear that up. So the supremum of the set, the interval 0 to 1. So if you think about it, the lower bounds on the interval 0 to 1 are don't have to be in the set itself. So remember, we defined the upper bounds and lower bounds as being real numbers and not being an x itself, or not needing to be an x, so it can be any real number. So a lower bound for this interval would be any negative number or 0, and the greatest of those lower bounds is 0 itself. And similarly, an upper bound for this set is any number greater than or equal to 1, and the least of those, aka the supremum, is 1. And let's write down what I said before. Now, to show that these are useful, let's try to take the maximum of 0 to 1. Well, for this interval, you can keep going as long as you want. If you think you have a max, you can just add a 9 to the right. So 0.9 is less than 0.99 is less than 999. You approach 1 but never reach it. So the maximum is defined to always be in the set. It's in this argument. So the maximum does not exist. Looking at another example, oh wait, before we go on to that other example, let's just write down what we said, that the supremums and infimums don't need to be in the set itself. So sup of x is not equal to x. We don't, or I'm getting confused here with what I'm writing or what I'm saying. So we don't insist that sup of x is in x, or the infimum of x is in x. They only need to be reals. As another remark, if x is not bounded above, we write sup of x is equal to infinity, and similarly we can write that if x is bounded, if we just replace the word above with below, and the inf of x is now I should just rewrite it, negative infinity. As a convention, we say the sups and infs are defined on the empty set, even though lower bounds don't really make sense, or upper bounds. Looking at another example, we define a set A being n over n plus 1, such that n is a natural number. So take f of x is equal to x over x plus 1. F prime of x is equal to, if you take the derivative here and use the quotient rule, x plus 1 minus x over x plus 1 squared. And those x's cancel out at the top to get 1 over x plus 1 squared. So f is increasing for x greater than or equal to 0. So f of 1 is less than or equal to f of 2, and so on. Therefore, the infimum of A is equal to the, so the infimum is the greatest, the greatest lower bound. So the least, the smallest thing it can be is f of 1, because f is increasing. as x goes to infinity. So if we just take it at the natural numbers, it's also increasing as n goes to infinity. So just to find it, we can get a real number. We have that infimum is a. Now, the limit as x goes to infinity of f of x is equal to 1. So, we can and if we note that f of x is less than 1 for all x greater than or equal to 0, now we conclude, sup of a is equal to 1. So we found the inf and the sup of the set. Okay, so another example. Take b is equal to negative x minus 1 squared plus 5, being a real number. If you plot it out, it looks like, I missed it. This, if you're a bit more careful with the sketching, maybe. The supremum here is equal to the maximum, and the infimum is, since it goes to negative infinity on both sides, just negative infinity. Okay, so another example, C, B, be non-negative real, so I'm going to write it this way from now on so it's more clear. Sorry if we're not explaining the old notation. Half of is less than cos y and less than to square root of 3 over 2. If we draw this out, you'll have some region here where it's greater than 1 over 2, and some region where it's less than square root of 3 over 2. And similarly, we'll have a region down at the bottom. Well, why did I draw it that way? So here the supremum is equal to positive infinity because y can keep going on, because it can just keep rotating and rotating and rotating around the circle. And because you can always satisfy this constraint, or this, But the infimum is defined because we have this greater than or equal to 0. So we're looking for when cos of x is equal to square root 3 over 2, and the least possible one, and that's going to be pi over 6. So the infimum is pi over 6. Finally, another example. Let A and B be positive real numbers. So that's the notation I want to use for positive real numbers. BD, bounded, that's shorthand for bounded. So A and B are bounded above, defined as AB is equal to elements AB, A in A, and B in B. Our goal here is to prove the sup of AB is equal to the sup of A times the sup of B. Let's draw parentheses everywhere. Proof. Take AB in A of B. So AB is in, by definition of the sup, or the least upper bound, less than sup A, sup B. And how did we get that? Well, let's write down some more stuff. We know A is in A, so A is less than or equal to A. And B is in B, sorry, that was wrong, sup of A. So B is less than or equal to the sup of B. And if we multiply these two inequalities together, then we get that AB less than or equal to sup of A, sup of B. And we can do this multiplication because we said they're positive numbers. So now we know, because of this fact, that sup of A and sup of B, this definition, or this inequality is exactly the definition of being an upper bound. So it's an upper bound for AB. And we know that the least upper bound, or sup of the set AB itself, must be less than any upper bound, so it must be less than or equal to, must be less, I'm mixing up words. The sup of AB is less than or equal to any upper bound, and those upper bounds include sup of A times sup of B. And so we have one side of this this equality. To show that they're equal, we can show one is less than or equal to the other, and the same thing is greater than or equal to the other, therefore they're equal. So as the next part of our subproof, of our proof, take A in A and B in B arbitrarily. We have that A is equal to AB 1 over B, and that's less than or equal to sup A B 1 over B, because AB is less than or equal to sup AB by definition. So sup AB is an upper bound for A, since it satisfies the definition of an upper bound. And so we have that sup of A, the least upper bound of A, is less than or equal to the sup of A, B, 1 over B. If we now rearrange, we have B is less than or equal to sup AB over sup of A. So this satisfies the definition of being an upper bound for B. And so it must be that the sup of B is less than or equal to this upper bound. Whoops. Made two mistakes, so those B's are supposed to be A's. Do not do math at 2:35 in the morning. So now multiplying both sides, sup of A, sup of B, is less than or equal to the sup of A, B. So now we have that sup of A. I always do that. I need to learn how to use this thing. I'm such a noob. Sup of AB is less than or equal to sup AB, and sup A, sup B is less than or equal to sup AB. Therefore, we can now conclude they're equal. And thus completing the proof. Okay, that is how you do that proof. Let's now move on to another proof, this time for a theorem known as the least upper bound principle. Every non-empty subset X of R, which is bounded above, has a supremum. And similarly, if we just replace everything related to bounding above with bounded below, we have the same thing. So find and replace the above with a below and the supremum with the infimum. We won't prove this, but it's good to know. As an example, take A being the interval from 0 to square root of 2, both sides being open, and intersect that with the rational numbers. Take a and a less than or equal to 100. The sup of a is not in the rationals. So the takeaway here are sups do not always exist. In R, they always exist in R. In Q. All right, that is it for this lecture.